Okay, cool.
Okay, so Min, you're first.
Yes, I will be the first to present.
Okay, then you ready to go?
Could you first give the introduction first?
Yep. Okay. So our first presenter is Min Lin. She is a PhD student in the Department of Electrical Engineering and Computer Science at the University of Tennessee, Knoxville. She has received her BSE degree from North China Electrical Power University in 2019 and her MS from UTK in 2021. Her research interests include medium voltage MMC converters and high voltage auxiliary power supplies.
Can you see my screen and hear me clearly?
Yep, all good.
Okay. My topic is high insulation voltage auxiliary power supply, and today I would mostly introduce this topic through like introduction, literature review, and the design and the results that I have done. And for medium voltage applications, it's like widely used in different kinds of converters, like converters for HVDC transmission, solid state transformers, electric vehicle fast chargers, solar inverters, and all kinds of stuff. And here the example I've shown here is medium voltage converter that is used to connect as an interface, like connecting the renewable resources to the microgrid. And so like there can be several of these converters, and the actual appearance of the converter is shown here. So as you can see, it incorporates many components like the voltage sensors and isolated power supplies. And another ongoing trend is the development of high voltage silicon carbide MOSFETs. So if you take power electronics classes, and you would find that high voltage silicon carbide MOSFETs has several advantages over silicon IGBTs, like higher blocking voltage, faster switching speed, and higher switching frequency. But it also brings forward like more disadvantages, like this higher blocking voltage would need a high insulation voltage auxiliary power supply, and this faster switching speed would cause high common mode noise. And here is a structure that I've shown here. Like basically, we have a gate driver circuit that is used to control the switching, like of this power modules. And if we put multiple of these power modules and gate driver together, it will be like large converter that I've shown in the last page. And this gate driver would need power itself. So it would need additional isolated power supply that would provide power to the gate drivers and signal isolator. Next comes the literature review. And so typically the auxiliary power supply is divided into two types. One is the local APS. So here you can see this local APS extracts power from the local bus bar. And so the insulation voltage required for this kind of APS is that of a one submodule bus bar voltage. And another type is the centralized structure, which means the APS would extract power from an external source instead of directly from the submodule bus, but this would increase this insulation voltage to 1/2 of the DC link voltage. So it will be the insulation voltage is increased. And to tackle this insulation issue, we try to follow the international standards to do the insulation design. So the insulation design, there are two parameters that gauge this insulation capability. One is the creepage distance, this distance along the surface between two objects, and another is the clearance distance. It's the distance in the air. So for different insulation voltages, it would have different creepage distance and clearance distance requirement. And this requirement is also affected by the purity of the air. If there is other dusts and like water drops in the air, it would need more clearance distance. And what is most commonly used in power electronics application, to do this insulation design, there are 3 categories. One is the usual magnetic isolation. So it's a transformer. There will be a core and primary windings and secondary windings and insulation material in between to maintain the insulation. And another is the wireless power transfer. As you can see here, the transmitting coils and the receiving coils are separated at a distance. So they use air as an insulation. And the third is using optical power, using optical power to support the gate driver. And this is limited because optical power is kind of limited at current stage. And what I'm mostly focused on is the insulation design of transformer. And we use high insulation material with extremely high dielectric strength. So this dielectric strength is much higher than that in the air. So this would reduce the clearance distance between the windings. And the materials uses silicon gel or epoxy, depending on application. And it just needs to fill the space between the primary windings and the secondary windings. So as you can see here in this picture, there will be a transformer and the PCBs are connected to the windings. And because this material, it has to be fully covering the whole transformer, and also you can put the material onto the primary and secondary board to enhance the insulation. Else you can just pulse the windings, only the windings are covered in the in silicon gel, but the PCBs are exposed in the air. So for this case, if the PCBs are exposed in the air, it will still needs to follow the requirements shown in last page. So in this case, it's 100 millimeter apart to support this 13 kV insulation. And also this would require a special procedure called vacuum pressure potting to extract the air and impurities out of the material. And so this is essential process to determine the quality of this insulation. And the second design criteria for this APS is the coupling capacitance. So if we assume that, as shown here, this is the silicon carbide MOSFET and it's switching on and off. And at this point, its voltage would deviates with the time. So it is called the dVdt. And for this very high speed switching silicon carbide MOSFETs, it can be as high as 100 volts per nanosecond. And this dVdt would, like if this dVdt travels in this circuit, it would exert a common mode noise current on this coupling capacitance. So this coupling capacitance is the capacitance between the like secondary side and the primary side of the APS, and this current would flow in a loop and back to the gate driver ground impedance, and so this current, like this noise currents, if we assume a 20 nanohenry ground plane inductance, that will be around like 0.44 volts of voltage peak. So this like noise voltage would possibly interfere with the operation of the gate driver. So to limit this common mode noise current and this voltage, we try to minimize this coupling capacitance as much as possible. And one way of doing it is to use a cylindrical capacitance model. So as you can see, it's essentially a toroidal core, and we have a primary cable, like primary winding in the center, and the secondary windings are on the cores. So the secondary winding coupling capacitance with the primary cable can be simplified to a cylindrical capacitance. And for this, the high insulation, just as I said, the high insulation requirement and also the coupling capacitance requirement will lead to low magnetic coupling between the primary side and the secondary side, and large leakage inductance. So this would, and also the control method is affected. And basically there are three types of regulation methods in this kind of converter. One is like using open loop regulation, and another is the primary side regulation. So there will be a primary side current control in flyback converter. And the third is a secondary loop regulation. But at current stage, the commercial optical coupler will not sustain this like 10 kV insulation voltage. And next I would go to the auxiliary power supply design. And here, as you can see, is the project that I've been doing. And there is like silicon carbide H bridge. So this is the module. And on top of it, it's the gate driver. And the auxiliary power supply is this this part here that supports the gate driver. And so this is the like final configuration. And let's get on to the details. So the topology I use is an LLC converter. So I would have like 4 outputs to support the 4 devices in a H bridge. But this is a little different from the conventional LLC because I would have 4 cores. And also the winding turns is a little different. The primary winding is only 1 turn, so it would go through all the cores. And here are the design parameters, and the voltage gain is a little different because I have 4 cores in series from the conventional LLC converter. And also the coupling capacitance design, basically on the right shows how you can calculate the capacitance based on the length and the distance of the windings. And there is a second approach is try to simulate in ANSYS Maxwell, like simulate. You can just assign the voltage like 20 kV on the secondary windings and 0 kV at the primary cable to see the capacitance between them. And the what's essential in the simulation is try to put the material relative permittivity, like the material characteristics, the same as the potting material that you've chosen, and like you can do the calculation simulation, and you can also directly measure it using an impedance analyzer. So like it can be a little inaccurate because it's a very small value, but still the value is much below the 5 picofarad requirement. And another part is to verify the insulation design. So I chose potting material that has a 18 kV per millimeter like dielectric strength, and I simulate this cross-sectional view of the transformer, just to see if the electric field distribution, like inside the cores and around the windings, to see if this field strength is would exceed this limit. And here shows 2 cases. The first case is where the windings are distributed uniformly around the cores, and the cable is placed exactly in the middle. And as you can see here, the field strength ranges from 0.99 to 3.98. And the second case is I try to separate the primary cable and secondary windings further apart. And so you can see here, this electric field is not uniform, that it would like further reduce the maximum electric field that this material would experience. So like in both cases, the electric field strength is much below this breakdown voltage, which means this transformer can like would be able to sustain that high voltage. And another issue is for the leakage inductance, because the cables and the windings are separated. So I try to simulate the leakage inductance to see how much this design would bring to the actual transformer. And another part is for the mechanical design, because this we have to securely like fasten the primary cable with respect to the core and the secondary windings in place, so that the coupling capacitances would be designed. And also, like this transformer needs a housing for the potting material. So because I have 4 cores in the topology, and this is like assembly case that I have designed. And for the results and discussion, so this is the actual converter that I have built, and here shows some waveforms under normal operation, and also like voltage balancing issue under different loads. So the voltage is quite uniform if the loads are similar, but if the loads are different, the voltage would deviate. And for fault operation, like because I have 4 terminals, so it's kind of challenging to determine if one output is short circuit, the impact on the other outputs. So the non-faulty terminal voltage gain would jump up, ramp up. And if there is an open circuit, the resonant frequency shifts away and the voltage gain drops. And this is the waveform in a short circuit fault. So as you can see, even though the waveforms are still sinusoidal, but it increases a lot and the output voltage just ramps up. And here is open circuit fault. Right? The voltage ramps up and the non-faulty output voltage drops. But this is kind of detrimental to the gate driver because the gate driver always wants a stable voltage input. And for conclusions and future work, so the conclusion is that like an auxiliary power supply is built, and we try to use vacuum pressure potting to achieve the 20 kV insulation, and the coupling capacitance is less than 5 picofarad to improve the EMI immunity, EMI resilience, and also like operation under different loading conditions. I think that's all from me today, and I probably ran out of time a little bit.
Okay. Does anybody have any questions? Because if not, I have 2.
Okay.
So is the auxiliary power supply, is the purpose of those to like give the converter ride through ability, or what are those doing exactly?
It's like the gate driver controls the switching of the devices, and the auxiliary power supply provides power for the gate driver.
Okay. Second, with the potting, is that something that you do to the components before you assemble the transformer, or is that something you do like after you have it assembled, then you pot it and then you put it in a vacuum?
Yes, after the assembly. So basically you need to fix everything in a tight case, and because after the potting, the material is like stuck inside, you cannot move it or adjust it.
Yeah.
So yeah.
So then I assume if that vacuum was to be breached, that you just have to throw the whole thing away.
Actually, like the vacuum just extracts all the air and bubbles out of the material. So that material will be like 100% pure. Like there will be no bubble inside to cause extra like breakdown.
Okay. All right. That is all I have for now.
Okay. Yeah, if you can contact me if you have further questions.
I'll take that as a no. Is Jingjing here?
Hello, yes. Yes, I'm here.
Okay, you ready to go?
Right. Yeah.
All right. So our next presenter is Jingjing Sun. She received her BS in electrical engineering from Xi'an Jiaotong University in Xi'an, China. I'm sorry if I butchered that.
Yes.
In 2016, and she received her MS in 2018 from UTK. She will receive her PhD in electrical engineering in May of 2022 from UTK. Her research interests include the applications of wide bandgap semiconductor devices, high efficiency converter design, and data center power distribution system modeling and emulation.
Okay, thank you, Vince. Hello, everyone. This is Jingjing. So today my presentation title is the GaN-based high-efficiency T-type totem-pole rectifier with full range, zero voltage switching control and reactive power transfer capability. So, well, first I will talk about the background and motivation of the research. Oh, by the way, could everyone see my screen? Okay, sure. Yeah. So, so for the power grid to achieve a high power transfer efficiency and maintain the voltage stability, reactive power compensation is necessary and important. So the basic idea is we want to correct the phase shift between the AC voltage and current with zero phase shift, so that the voltage and current are in phase. In this way, the real power will be used, will be fully used, and the reactive power is minimized. The traditional power compensators include the static VR compensator and the static synchronous compensators. They can provide a flexible reactive power compensation, but they are centralized bunking power compensators with high cost and high power loss. On the other hand, the grid support with load participation is a cost-effective approach to control the power grid, like critical loads such as data centers and telecommunication power supplies. There are advantages in large power consumption and flexible loading. So the front-end power supply, especially the rectifiers, can provide fast and flexible reactive power. So in this way, the front-end rectifiers can be used for dual purpose. That is, not only deliver the active power transfer for the load, but also generate or absorb the reactive power to support the grid. So for rectifier, for a converter, let's say for the traditional PFC rectifier, the operation range is only the positive part of the active power axis. Well, when operate it with the reactive power, the operation range can be enlarged into a half circle. Well, research work has been made to implement such reactive power on the front-end rectifier. For example, here, the real power and reactive power are controlled separately in the D and Q axis. However, the limitation is the existing work concentrates on the reactive power operation with the traditional silicon-based PWM converter in hard switching. So the efficiency is not high, and also the switching frequency is almost below 100 kilohertz, which results in low power density. Well, on the other hand, the gallium nitride devices based Totem-Pole PFC rectifier with critical conduction mode operation and soft switching control has been studied widely and is treated as a promising candidate for the front-end rectifier. So such rectifier has been demonstrated with 99 peak efficiency and high power density in different applications. So if we can use such high efficiency rectifier to achieve the reactive power compensation, then the power loss for the reactive power compensation can be reduced a lot, and also the bunky expensive centralized power compensator is not necessary anymore. So here shows the simulation waveform of the CRM Totem-Pole rectifier operating with the reactive power that is at 0.8 PF. So there are two implementation challenges at the AC line zero crossing. One is the very high peak switching frequency at the zero current zero crossing point. The other one is at almost zero switching frequency at 0 voltage, 0 crossing point. So this will be a challenge for implement the full range ZVAS control as well as the reactive power transfer. And so far, there is no research to fully design and develop such a CRM rectifier with GaN devices, source switching control, and the reactive power transfer. So research gap exists on the analysis and design of the GaN-based CRM rectifier with both source switching control and reactive power regulation. So that's what I did, what I'm doing in the research work. So a GaN-based CRM rectifier with high efficiency and reactive power transfer capability is developed. So this is the proposed topology of the GaN-based CRM T-type Totem-Pole rectifier. So compared to the traditional Totem-Pole rectifier, the bidirectional switch S5 is inserted between the DC link capacitor and the middle point of the silicon MOSFET face-like. The rectifier will operate in 2 operation modes. The first one is the Totem-Pole mode, that is the same as the traditional Totem-Pole rectifier, where the second one is the T-type mode. And intermediate voltage, input voltage boundary is defined to distinguish these 2 operation modes. So when the input voltage absolute value is above the boundary voltage, the S5 device will turn off. So the rectifier is the same as the traditional Totem-Pole rectifier, operating with the unipolar modulation. Well, on the other hand, when the input voltage absolute value is below the boundary voltage, as highlighted here, S5 will be turned on and S3 and S4 are turned off. In this way, the rectifier operates similar to the bipolar modulation, where the inductor voltage actually is dominated by the output voltage. So with this, we need to develop the full range ZVAS modulation. So with the reactive power, the input voltage and current are no longer in phase. Therefore, the ZVAS modulation at 4 quadrants of the input voltage and current is proposed. Well, during the Totem-Pole mode, well, the converter just operates in the same way with as a Totem-Pole rectifier. Here we will discuss it only in the positive half-life cycle. So when the input voltage and current are in the same polarity, the S1 and S2 are GaN devices operating at the high switching frequency mode, and S3 and S4 are silicon MOSFETs just switched in the line cycle for the rectification. The S1 device is the synchronous rectification device. It can achieve natural DVS within the whole range for the input voltage. However, for the S2, the active switch, it can only achieve natural DVS when the input voltage is lower than half of the output voltage. Well, when the input voltage is higher than half of the output voltage, the inductor current is not enough to fully discharge the capacitance, output capacitance of the device. Therefore, we need to extend the ZVAS operation range. So here the method is we purposely extend the conduction time of S1. As a result, a lower negative current is achieved, which is able to fully discharge the output capacitance before S2 is turned on. In this way, the VDS S2 can resonate to 0 before turn on S2, and the ZVAS turn on is achieved so that the switching loss is minimized. Well, on the other hand, when the input voltage is in the opposite polarity with the input current, then the active switch at S1 can always achieve DVS naturally. However, S2, the active switch S2 can achieve natural DVS, while S1 will achieve valley switching, that is partial hard switching, when the input voltage is lower than half of the output voltage. Based on the same rule, we purposely extend the convention time of S2 so that the DVS operation range is extended and the full range DVS turn on is maintained. Here shows the modeling of certain key parameters for the device modulation. I will not talk about it in detail. And on the other hand, during the T-type mode, S3 and S4 turn off, and S5 is always conducts. So still S1 and S2 operates in the high switching frequency. When the input voltage and current are in the same range, are in the same polarity, the synchronous rectification device S1 can always achieve DVS naturally, while the S2 cannot achieve DVS naturally. So we need to extend to ensure a lower valley current to extend the device range. Well, on the other hand, when the input current is in the opposite polarity of the input voltage, both of the two GaN devices can achieve DVS naturally. So based on this, actually we could derive the whole full range device modulation at both the positive half-line cycle and negative half-line cycle, and also for both unity power factor operation and non-unity power factor operation. And here shows the analytical waveforms of the AC voltage, the inductor current envelope, and the switching frequency. So there is still one problem, that is the very high switching frequency at the zero current, at the AC current at zero crossing point. So a frequency limitation method is also derived, where the peak switching frequency can be limited below the target value. Here, the switching frequency is limited below 800 kilohertz. And with this, a control strategy is developed to achieve the full range device operation, as well as the reactive power transfer. So the instantaneous real power and the reactive power are calculated based on the condition, the input voltage and current. And then the real power and the output voltage are regulated through the outer voltage loop and generate the ID reference, that is the current reference. And the reactive power is controlled through the outer reactive power loop and generates IQ reference. Finally, the AC current reference is composed of the ID reference, IQ reference, and the according phase angle. And then based on the model-based real-time calculation, we could have calculated the switching time intervals and further generate the PWM signal to control the converter. Zero current detection signal of the inductor current is used to synchronize the PWM signal and the inductor current. So based on this, a hardware prototype of the proposed GaN-based T-type Totem-Pole rectifier is built. This is the prototype, and it is specified with the 277 volt AC voltage and the 480 volt DC voltage. And the power rating is at 1.6 kVAR, and switching frequency ranges from 170 kHz to 800 kHz. Also, the 650 volt gallium nitride devices are used for the rectifier. So here shows the full load experimental waveform at the unity power factor. As can be seen, the input current is regulated in phase with the input voltage, and also the output voltage, DC voltage, is well regulated at 480 volts. The inductor current is regulated in critical conduction mode, where the full range device operation is achieved to minimize the switching loss. As a result, the tested efficiency at full load is 98.9%, and the input current THD is 3%. And the rectifier is also tested with different non-unity power factor, as shown here. The input voltage, input current, and output voltage waveforms. Here is the case at 0.94 leading power factor. This is at the 0.94 lagging power factor, and this is at the 0.94 leading power factor, and the last one is at 0.87 lagging power factor. So all the testing points achieve the efficiency above 98.5%, and the current THD is below, the input current THD is below 5%. So we also want to achieve flexible regulation of the rectifier. So dynamic operation is also demonstrated. Here shows the dynamic operation below between the lagging PF and the leading PF. The rectifier reference is linearly changed within 4-line cycle. As a result, the phase shift between the input voltage and current is gradually adjusted within the 4-line cycle and without current overshoot. We also tested the rectifier in dynamic operation at half load. Here we give a step change in the rectifier reference, and the rectifier performs a faster dynamic response within the 2-line cycle. This depends on the loop bandwidth of the rectifier loop at the 30 Hertz. Well, if you want to achieve a faster dynamic response, you can further improve the control bandwidth. So in conclusion, this work, high efficiency single phase GaN-based rectifier with rectifier transfer capability is proposed and demonstrated. This can be used in front-end power supplies as an efficient alternative to centralized power compensators for reactive power compensation. Well, T-type totem-pole rectifier topology is proposed, and full range device modulation for both the unity power operation and the non-unity power factor operation is proposed for the CRM rectifier. Well, also to implement the control, a digital-based control scheme is developed. Finally, the analysis and design is demonstrated and verified by a hardware prototype, which is demonstrated with full range device operation, high operating efficiency, and flexible reactive power regulation. Well, finally, I would like to thank all the sponsors for their support, and also thank you for your listening and welcome any questions.
All right, thank you.
Thanks.
I have 2 questions.
Sure.
I'm not a power electronics guy, so excuse me if these are obvious. What is the difference between soft and hard switching?
You mean difference between soft switching and hard switching?
Yes.
Oh, yeah. So for power converter, we will need to use the power devices, basically, for example, the MOSFET. So it will have both the power loss will include the conduction loss and the switching loss. Actually, for the converter, switching loss will be a large partial part of the loss. And for hard switching, the switching loss, the turn on, both the turn on switching loss and turn off switching loss are there. So, well, with the soft switching, we can either turn on or turn off the device with 0 voltage or with 0 current. In this way, either the turn on switching loss or turn off switching loss is reduced or fully eliminated. So that's why we can reduce the switching loss a lot and further reduce the total power loss and increase the converter efficiency.
Okay, then that makes sense. My second question is, what is ZVS modulation? I've never heard of that before.
Yeah. ZVS means zero voltage switching. That is one of the methods for software switching to improve the efficiency. Yeah.
Okay. That is all I had. Does anybody else have any questions?
I had a question. This is a little out of my research area, but you covered a lot of information here, and I was wondering, as you were, working through these projects, what was your biggest challenge, and how did you overcome it?
Yes. So I think the first challenge will be, well, for the research, like in my case, I need to first find out the research gap and what is the research challenge in that. So here, my challenge will be, it has the control and implementation challenge for the rectifier operation as well as ZVS control at the same time. So with this, you need to figure out either through the topology or through the control method, just generate a new method to solve it. And then another challenge will be, you need to verify it. Verify your theory, your design theory is correct. So for the building of the hardware prototype and also testing out, it is time consuming and also need the debugging techniques, I would say. Yeah.
Thank you.
Thank you for your question.
All right. Anybody else? I will take that as a no. All right. Thank you to our presenters, and I guess everybody have a good weekend. Dr. Chen's already left, so she said see you in 2 weeks. All right. Thanks, everybody.